So in this question, we have to calculate the range of the expression f of x, which is defined as x square plus x plus 1 divided by x square minus x plus 1. All right. It's also given that x belong to the set of real numbers. Cool. So this is the expression for f of x given to us in the question. It's also given that x belong to the set of real numbers. All right. So what do we do next is equate this to y and cross multiply. If we do that, we get x square plus x plus 1 is equal to x square y minus xy plus y. All right. Now, if I rearrange these terms, what we will get is x square multiplied by y minus 1 minus xy minus x plus y minus 1, and this is equal to 0. All right. Now, if I further simplify this, I get x square multiplied by y minus 1 minus x multiplied by y plus 1 plus y minus 1 is equal to 0. We have a quadratic in x. Now, this quadratic will be defined when the coefficient of x square is non-zero or y minus 1 is not equal to 0. If y minus 1 is not equal to 0, y is not equal to 1. So what we are going to do is solve this complete question keeping in mind that y is not equal to 1. And at the end, we will check if for y is equal to 1, are we going to get any real x or not? All right. As you can see, we have a quadratic in x and x belong to the set of real numbers. That means this quadratic will have real roots, or we can say d is going to be greater than equal to 0. Let's calculate the expression for d. We have y plus 1 the whole square minus 4 times y minus 1 times y minus 1, and this is greater than equal to 0. If I simplify it further, I get y square plus 2y plus 1 minus 4y square minus 4 plus 8y greater than equal to 0. If I simplify it further, I get negative 3y square plus 10y minus 3, and this whole thing is greater than equal to 0. So we have an inequality minus 3y square plus 10y minus 3 greater than equal to 0. If I multiply this complete inequality with minus 1, we will have to reverse the inequality sign. So what we get is 3y square minus 10y plus 3 is less than equal to 0. All we have is a quadratic in y. We will split the middle term to factorize it. So what we will get is 3y square minus 9y minus y plus 3, and this is less than equal to 0. We'll get two factors here, y minus 3 multiplied by 3y minus 1, and the product of these two factors is less than equal to 0. Two factors suggest two critical points. That's correct. 1 by 3 and 3. Now, if I put y is equal to 4 in the expression, what I will get is 1 multiplied by 12 minus 1, which is equal to 11 and greater than 0. That means we'll start with positive. The wavy curve will start with positive. About 3, it will change to negative. About 1 by 3, it will change to positive again. Now we want the interval for which this expression is less than equal to 0. That means y belong to the interval 1 by 3 to 3, including both 1 by 3 and 3. All right. Now from this interval, we have to subtract 1 because we solved for this complete inequality keeping in mind that y is not equal to 1. So this is the values of y that are acceptable by us. All right, now let's check for y is equal to 1. If I equate this to y and put the value of y as 1, I get x square plus x plus 1 is equal to x square minus x plus 1, or we can say 2x is equal to 0 or x is equal to 0. As for y is equal to 1, we are getting x is equal to 0, which is real x, or we can say acceptable value of x. That means y belong to the interval 1 by 3, comma 3, including both 1 by 3 and 3. So the one value of y, that is 1, we excluded earlier. We will include it because when y is equal to 1, x is equal to 0, and this is our final range of f of x, which is given by option A here. So in this question, we have been given a quadratic equation x square plus ax plus b is equal to 0. In the question, it's been given that this quadratic equation has two roots, a and b, such that they both are non-zero distinct numbers. All right. Now we have to find out what is the least value of the quadratic polynomial defined as x square plus ax plus b. Cool? So this is the quadratic equation given to us in the question. It's been given that it has two roots, a and b. And what do we know about a and b? We know that both a and b are non-zero distinct numbers. All right. So what we are going to do next is compare this given quadratic equation with our standard quadratic equation, capital AX square plus capital BX plus capital C equal to 0. Now, you must be wondering, why did I take capital AX square plus capital BX plus C equal to 0? It's because we are already having small a and small b in the given quadratic equation. So just to avoid that confusion, I have taken the standard quadratic equation with capital constants. So we have capital AX square plus capital BX plus capital C equal to 0. Now, if I compare these two given quadratic equations, I'll get capital A is equal to 1, capital B is equal to A, and capital C is equal to small b. Now, using this, we have to find out the least value of x square plus ax plus b. All right. So what I do next is I calculate the sum of the roots. Sum of the roots would be a plus b, and this is equal to negative of capital B divided by capital A. Now we know that capital B is small a and capital A is 1. If we put those values in this equation, we will get a plus b is equal to negative of a. Now similarly, we can calculate the product of the roots. It would be a times b, and it is equal to capital C divided by capital A. Now we know that capital C is equal to small b and capital A is equal to 1. If we put those two values here, what we will get is a multiplied by b is equal to small b. So now we have two equations. Yes. We have two variables. Yes. We just have to solve for small a and small b. Now I'm going to start with the second equation right here, because it's easy and simpler to solve. All right. Now here, what is the first instinct that we get here? To cancel out b. But we do have to check whether b is a non-zero number or not. But yes, it's a non-zero number because it's given in the question that both a and b are non-zero distinct numbers. So if b is a non-zero number, we can simply cancel out b. And if we do that, we get the value of a as 1. So what's the next step? Put the value of a equal to 1 in the other equation here. If we do that, we get the value of b as negative 2. All right. So we have got a equal to 1 and b as negative 2. That means we have got a quadratic polynomial. Let me define it as f of x, and this is defined as x square plus x minus 2. So we have our quadratic polynomial here, which is f of x is equal to x square plus x minus 2. Now, as you can see that a, which is the leading coefficient or the coefficient of x square, it is equal to 1 and greater than 0, we will get an opening upward parabola. If we get an opening upward parabola, we can say that the y-coordinate of the vertex will give us the minimum value of the quadratic polynomial x square plus x minus 2. All right. So what do we have to do next is calculate the y-coordinate of the vertex. So we know that the y-coordinate of the vertex is given by negative d divided by 4 times a. Now this is equal to negative of b square minus 4ac whole divided by 4 times a. Now what is the next step that I have to do? Just substitute the value of capital A, capital B and capital C in this expression right here and find out the minimum value of the quadratic polynomial. So what I will get here is negative of 1 square minus 4 times 1 times negative 2, and this whole thing is divided by 4 times a. If I further solve this, I will get negative of 1 plus 8 divided by 4, which is equal to negative of 9 by 4. So we have got our minimum value of the quadratic polynomial, and the minimum value of the quadratic polynomial is negative 9 by 4, which is option C. All right. So in this question, we have been given a quadratic equation k plus 1 times x square minus 3kx plus 4k equal to 0. And we have to find out the range of k for which both the roots of this quadratic equation are greater than 1. All right. So this is the quadratic equation given to us in the question, and we have to find out the range of k for which both the roots of this quadratic equation are greater than 1. So if I assume that this quadratic equation has two roots, alpha and beta, then I have to find out the range of k for which both alpha and beta are greater than 1. All right. Now for this quadratic equation to be defined, k plus 1 should not be equal to 0, or we can say that k should not be equal to minus 1. If k is not equal to minus 1, we can divide this complete equation with k plus 1. What we'll get is x square minus 3k divided by k plus 1 times x plus 4k divided by k plus 1 equal to 0. All right. Now, if I define a quadratic expression f of x as x square minus 3k divided by k plus 1 times x plus 4k divided by k plus 1, then the graph of f of x will look like this. All right, where both the roots of the equation f of x equal to 0 are greater than 1. Now, what are the conditions that we have to take? First, d greater than equal to 0. Second, f of 1 is greater than 0. And the third condition would be x coordinate of the vertex should be greater than 1 as well. So we get minus b by 2a greater than 1. So these are the three conditions. Once we solve these three conditions, once we solve these three inequalities, we have to take the intersection at the end to find out the final range of k for which both the roots of the equation f of x equal to 0 are greater than 1. All right. So starting with the first condition, d should be greater than equal to 0. What we'll get is negative of 3k divided by k plus 1 the whole square. All right, plus, no, it would be minus of 4 times 1 times 4k divided by k plus 1, and this whole expression should be greater than equal to 0. All right. Now, if I simplify it further, after multiplying this complete inequality with k plus 1 the whole square, can I do that? Let's check. Earlier, we had said that for the quadratic equation to be defined, k plus 1 should not be equal to 0 or k should not be equal to minus 1. So it's safe to multiply this complete inequality with k plus 1, all right? But in this case, we are multiplying this inequality with k plus 1 the whole square. And we know that square of any number will always be greater than 0. So we are multiplying this complete inequality with a positive number, and keeping in mind that whenever we multiply an inequality with a positive number, the inequality sign doesn't change. All right, so what we'll get is 9k square minus 4 multiplied by 4k multiplied by k plus 1, and this should be greater than equal to 0. On further simplification, what we'll get is 9k square minus 16k square minus 16k greater than equal to 0, which can be written as negative 7k square negative 16k greater than equal to 0. Now let's multiply this complete inequality with minus 1. But minus 1 is a negative number. If you are multiplying a inequality with a negative number, the inequality sign will reverse. If it was greater than equal to 0 earlier, it will become less than equal to 0. So what we'll get is 7k square plus 16k less than equal to 0. And this can be further factorized and written as k multiplied by 7k plus 16 less than equal to 0. How many factors are there? There are 2 factors. If there are 2 factors, there will be 2 critical points on the number line, and this is how it will look. Now, if I put any number greater than 0, say for example, k equal to 1 in the expression k multiplied by 7k plus 16, what I'll get is 1 multiplied by 7 plus 16, which is a number greater than 0. So we'll start with positive. About 0, it will change to negative. About negative 16 by 7, it will change to positive again. But I'm looking for the interval where the expression k multiplied by 7k plus 16 is less than equal to 0. So what we'll get is k belonging to the interval negative 16 by 7 to 0, including both negative 16 by 7 and 0. All right, but earlier we had seen that k should not be equal to minus 1, so I will have to subtract minus 1 from this interval. Alright, now moving on to the second condition, f of 1 greater than 0. What is f of 1? It would be 1 minus 3k divided by k plus 1 plus 4k divided by k plus 1, and this should be greater than 0. If I further simplify this, I'll get 1 plus k divided by k plus 1, and this should be greater than 0. We can further write it as k plus 1 plus k divided by k plus 1, and this is greater than 0. On further simplification, we'll get two factors, 2k plus 1 divided by k plus 1, and they are greater than 0. Their division is greater than 0. Alright, so there are two factors, 2k plus 1 and k plus 1. If we have two factors, we'll get two critical points on the number line, and the two critical points would be minus half and minus 1. Alright, now if I put any number greater than minus half in the expression of k, say for example k equal to 0, I'll get 1 divided by 1, which is clearly greater than 0. That means we'll start with positive. About minus half, it will change to negative. About minus 1, it will change to positive again. But I'm looking for the interval where this expression is greater than 0. So what we'll get is k belonging to the interval minus infinity to minus 1, open at both, union minus half to infinity, open at both. Alright, so we have got the interval for the second condition. Moving on to the third condition, negative b by 2a greater than 1. What we'll get is 3k divided by twice of k plus 1, and this should be greater than 1. Now, if I take 1 from right hand side to left hand side of the inequality, I will get 3k divided by 2k plus 2 minus 1 greater than 0. And if I further take LCM, I'll get 3k minus 2k minus 2 divided by twice of k plus 1, and this should be greater than 0. This can be further simplified and written as k minus 2 divided by twice of k plus 1 greater than 0. Alright, so how many factors are there? There are two factors, k minus 2 and k plus 1. If there are two factors, there would be two critical points, and the two critical points are minus 1 and 2. Alright, now if I put the value of k as 3 in this expression, I will get 3 minus 2 divided by 2 multiplied by 3 plus 1, which is equal to 1 by 8, and this is greater than 0. That means we'll start the wavy curve from positive. About 2, it will change to negative. About minus 1, it will change to positive again. Alright, now if I find out the interval for which this expression is greater than 0, I'll get k belonging to the interval minus infinity to minus 1, open, union 2 to infinity, open at 2 and open at infinity. Alright, so this is the interval for the third condition. We solved for the three conditions, we got the three intervals. Now let's find out their intersection. So this is the first interval where k belongs to the interval minus 16 by 7 to 0, excluding minus 1. The second interval is minus infinity to minus 1, union minus half to infinity, excluding both minus 1 and minus half. The third interval is minus infinity to minus 1, union 2 to infinity, excluding both minus 1 and 2. Alright, now if I draw these three intervals on the same number line, what I'll get is, so this is the number line. What are the critical points? Minus 16 by 7 and 0. Alright, so this is the interval lying between minus 16 by 7 and 0. But we have to subtract minus 1. So I will put an open circle at minus 1. Now if I draw the second interval on the number line, this is how it will look. Alright, so we'll get this region where both minus 1 and minus half are not included. And if we draw the third interval on the number line, this is how it will look. All right, now we have to look for their intersection. And this is the region where all three of them are intersecting. If I write this region in the interval form, it would be k belonging to interval minus 16 by 7 to minus 1, excluding minus 1 but including minus 16 by 7, which is same as option A here.
For more videos and live lectures on the JEE, click on the subscribe button now.